In this video, we're going to talk about the geometric interpretation of the integral. Just make sure you've watched the previous video on the introduction to the integral. So as in that video, we're going to be talking in the framework of taking a trip on a one-dimensional line over some time interval. So let's say we're moving around in one dimension and we're starting at time A and ending at time B. And our velocity at a particular time is going to be v of t. Now we talked in the last video about how you can compute the distance covered in this time interval with this velocity function. And that's what's called the integral, the definite integral from a to b of the velocity function with respect to t. And the way we do this is distance is velocity times time. And so velocity, so here we have this complicated looking formula, but if you start on the inside, it's just velocity times time. Okay, velocity times the time interval involved. And here these time intervals, we take our big time interval from A to B and we chop it up into a bunch of very tiny pieces. And on each of these tiny pieces, the velocity is basically constant. It's very close to constant. So we can just take the velocity at some time and use that as a representative of the velocity on the whole interval to get an estimate of the distance covered in that small little time interval. We sum that up over all of the time intervals, and that gives us an estimate of the distance that we covered in the time interval AB, and that approximation becomes exact as n goes to infinity. What we're going to do here is develop a picture that can help us visualize this formula and give some intuitive geometric content to it. So we start with, so here's the situation. We have in this picture the graph of the velocity curve. Okay, so this orange curve is v of t. So that's the curve in orange here. So when v is positive, we interpret that as we're moving forward. Okay, so positive velocity moving forward along our line. Okay, so velocity positive moving forward. And down here where the velocity is negative, we're moving backwards along the line. So along our one-dimensional line, we could move forward, come to a stop, and reverse if we want. Right? We drop something along the way, we want to go back. So we're allowing forward and backward motion along the line. So we'd be moving forward in this part, backward here, forward again. Okay, and here's our time interval. So we're graphing velocity as a function of time, and our time interval is from A to B. And so here's the geometric picture of what we talked about last time. So our interval from A to B, we chop it up into a bunch of different pieces, right? I got a lot of pieces here. So I've chopped it up evenly into these pieces. The width is delta t. I don't know what the n is. There's a fairly large n here. You could count it up if you'd like. So that's what the n is the number of these little intervals here. They're all, each of width delta t. And what we talked about last time is that in each of these little intervals, so in each of these little intervals, you can look at the velocity. The velocity doesn't vary much in that interval, right? It varies a lot over the big interval. It doesn't vary very much in the small interval. So if I pick a particular time and I look at the velocity of that time in that interval, the velocity at that particular time is not that far off from the velocity at any other time in that little interval. So if I do the velocity here times the delta t, which is the width of the interval right here, that velocity times the time elapsed, that gives you an approximation of the distance that's covered in this part of the journey. And we can interpret this geometrically, because the velocity, right, so this velocity times delta t, well, delta t is the width of this little rectangle here, whereas v of t, right, so we took this point here, we applied the function v, so we came up to this height, right, so v of t is just the height of this rectangle. So v at this ti star, this fancy looking thing, so just the velocity times the delta t is just the area of this rectangle, this green rectangle here. Okay, so that's what I've written here. We just have velocity given by this function, that's the height of the rectangle, times delta t, that's the width, and so we have height times width, that's just the area of that rectangle. Now we also have parts of the velocity curve that are under the t-axis. like right here. So if we take this this time in whatever this interval is here and look at the associated velocity, that's now a negative velocity. So when we do the velocity times delta t, that's going to be a negative number, right? So the v at that particular time, that's not going to be the height of this rectangle, because height, we usually think of it as positive. It's really going to be the negative height, or the so-called signed height. Okay, so it's the height of this rectangle, but we give it a negative sign because it's below the axis. Right? So if we look at the velocity times the delta t for this particular rectangle, what we get is signed height times width, or signed area of this rectangle. Okay, so basically signed area of a rectangle means we count the rectangle's area as positive if the rectangle is above the x-axis, or t-axis in this case, and negative if it's below the t-axis. Okay, so basically each of these rectangles, the v, the velocity times delta t, it's the signed area of the rectangle that quantity is recording. Okay, so we have a sort of dual interpretation of this term here. We can either think about it as a distance, or a velocity times a time, a distance, which would be the approximate distance that we're covering in this particular time interval, or we can think about it as a signed area. Okay, so that tells you what this, without the sum or the limit, just what this little piece means here. Right, so on each of these little intervals here, we're going to construct a rectangle, right? Just pick a time in here and look at the associated velocity. That's going to give you the height, and you construct a rectangle. So that's all we did here. So each of those is just the signed area of a rectangle. Now what we want to do is add in the sum. So when we add in the sum, well, we're summing over all of those little subintervals, right? So in each little subinterval, we have a time and a velocity that's representing the velocity over that little part of the journey. And so the velocity times that delta t, that's going to give us the approximate distance we covered in there. But it's also going to be the signed area if we think about it geometrically. And so for this one, we get this area, for this rectangle. For this one, we get this rectangle. For this one, we get this rectangle. We just go along. Over here, we have rectangles that have negative signed area. Right? And then we move over here, we have rectangles that have positive signed area again. So we're just going to, when we add up the velocity times the delta t, the positive ones, that's going to be here and here. And then we're going to have those positive ones, and we're also going to have negative ones. All right, so for all of the times that are in these subintervals, we're going to have negative areas, right? We're going to have negative signed areas. And so when we add up that sum, we get these positives, and then some negative, and then some positive. And to bring the limit in here, once we take this limit, you can kind of see that, right, in this picture, I mean, basically these rectangles are sort of crudely approximating the shape of the graph itself. So you can probably see that this signed area of the rectangles, so the total signed area of all of these rectangles, it's approximating the signed area under the graph of v of t itself. And so that's what this looks like here. So here's v of t. The signed area under the graph of v of t is this. So you take the area here, which I'm denoting as 1, so that's going to count as positive. The area here, which I'm denoting 3, that's also going to be positive. You add those together, and you subtract the area that I'm labeling 2 underneath of here. Right, so it's signed area because everything that's above the axis gets a positive sign, and the stuff below the axis gets a negative sign. Okay, so your integral, which is the limit, and so above here, we had just the sum without the limit, right? That gives you the total signed area of the rectangles. When you pass to the limit, as n goes to infinity, you get the integral, which is here. And then those rectangles become very skinny, and it's no longer approximating the shape of the curve. It really exactly matches the shape of the curve. And you get positive, the part of the function which is above the x-axis, you get positive area. The stuff that's below the x-axis, you get negative area. And you can see sort of why that happens. As n increases, the rectangles get skinnier and skinnier. So these skinny rectangles, there's no longer very much overhang, right? So the rectangles are a crude approximation of the graph. They overhang the graph. They also underhang the graph. But the skinnier those rectangles get, the smaller the overhang and the underhang. And so that error in your approximation becomes very small when n goes to infinity, and you get the area, the signed area under the graph exactly. So this here really is the main point of this video, that the integral of your velocity function from a to b, which we interpreted physically last time as the distance covered, the distance covered in this time interval from a to b, you can interpret it geometrically as signed area. Okay, so you get area, the stuff that's above the t-axis or the x-axis, whatever the case may be. So in this case, we have t. The stuff above the t-axis is counted as positive, and the stuff below the t-axis is counted as negative. If you add up those areas with the appropriate signs, that is what the integral is giving you. Okay, so geometrically, the integral is signed area. So I thought it might be a good idea to end by connecting this picture of signed area to the discussion we had in the Introduction to Integral video, where we discussed the physical interpretation. So in this picture, our integral, our definite integral from a to b of the velocity function here, it's the area under this first part that's above the t-axis minus the area that's under the t-axis between the points c and d here, and then plus the area above the axis again between d and b. Okay, so that's the geometric interpretation we just talked about. We can also think about this in the physical way that we were discussing in the previous video. So this first part here, right, you can see the velocity is positive. We're above the t-axis here, so the velocity is positive, and so that means we're moving forward, right? So what this 1 here is, the area under here, that's the total distance covered from A to C, right? So the area under under the part of the graph from A to C, that's the integral from A to C, and that is just the forward distance. That's just the distance covered in that particular time interval. Okay, so this is the distance that we've covered in the time interval from A to C, and it's forward distance because the velocity is positive. But now if we move to this second part here between C and D, now our velocity is negative, right? So this part of the, so this negative area here, that represents the distance covered going backwards in the time interval from C to D. Okay, so if we measure, so in this part, our velocity is negative, we're going backwards along our one-dimensional line. And if we measure that total backwards distance that we've gone, we would be subtracting that out, right, in our total of how much distance we covered in this full interval from A to B. We'd have to subtract that backwards part out. Okay, so that backwards part getting subtracted out, that matches up with the interpretation with signed area. So below the axis, the area counts as negative because in the physical interpretation, our motion is backwards. Okay, so we're sort of we're not accumulating more distance, we're losing distance. We're going back the way we came. And then in the last part where we're above the axis again, the area 3, that would be the forward distance covered in that time interval. Okay, and we can express each of these. The forward distance covered between A and C, that's just the integral of our velocity function from A to C. This negative distance that we covered from C to D, that's just the integral from C to D of our velocity function. And then the forward distance, again, from D to B is written as this definite integral. So in summary, the integral, we basically, when we're talking about the velocity function, the integral from A to B, we developed two interpretations of it. So in this video, it's signed area under the graph of the velocity. And in the previous video, we talked about it as the total distance covered in a particular time interval. And this total distance can be positive if the overall motion is towards the right, or it might be negative if our overall motion is to the left. If we're going backwards more than we're going forward, our total distance could be negative. Okay, so we have either signed area could be positive or negative depending on whether there's more positive area, more negative area, and total distance covered, this could be positive or negative depending on whether we were moving forward more than we were moving backward or not.